Hello everyone, my name is Stu Adler. Welcome back to Introductory Lectures in Thermodynamics. During the last episode, I introduced the first law of thermodynamics for closed and open systems. What I'd like to do in this episode is begin applying the first law toward mapping out the internal energy of real substances, including an accounting of potential versus kinetic energy. The use of the first law as a theoretical formalism for this purpose is known generally in thermodynamics as first law analysis. Before diving in, I'd like to say a few words about why we need a theoretical formalism involving the first law for quantifying internal energy. When we simulated a 2D Lennard-Jones fluid, it was not hard to quantify kinetic and potential energy. In that case, the average kinetic energy per molecule was simply temperature multiplied by a constant. Meanwhile, potential energy, under many conditions, obeyed the van der Waals mean field theory, so it could be related to molar volume, which is measurable. So what's the big deal? Why can't we just add these two terms together and be done with it? We actually have two problems. The first is that the mean field theory assumed by the van der Waals equation for potential energy is a gross oversimplification of what's really happening. Although it can give us a ballpark estimate, it's usually not good enough to accurately quantify potential energy. Even the Lee-Kessler equation of state, which is dead-on accurate for many gases and supercritical fluids, breaks down when gases condense to liquids or solids, or form complex structures and mixtures. Molecules can also react, which involves yet another form of potential energy. So we really need some way to quantify the potential energy that goes beyond the corresponding states principle, and does not rely on the accuracy of a particular model. The other problem is that the total intramolecular kinetic energy is not really linearly proportional to temperature. This is because real molecules obey quantum mechanics, not classical physics as assumed in our Lennard-Jones simulation. For example, those of you currently taking Chemie 498 have been studying the problem of a particle in a box. Shown here is the time-dependent solution to Schrödinger's equation for a 2D Gaussian wave packet inside a small two-dimensional box. As you can see, it closely emulates a classical particle like the ones in our 2D Lennard-Jones fluid. A consequence of this is that for translational degrees of freedom, molecules behave classically at ordinary temperatures. One way to visualize this is to imagine the individual energy levels for the x, y, z translational modes of a molecule. As you'll learn in PChem or Chemie 457, the equilibrium occupation of these energy levels at a given temperature follows a Boltzmann distribution, depicted here in blue. For any macroscopically sized box, the translational levels are so closely spaced that the distribution is smooth and continuous, corresponding to the classical limit. Thus, for monatomic molecules like helium, argon, or other noble gases, changes in temperature are directly linked to changes in kinetic energy by a factor of 1/2 R per translational mode, as predicted by the classical theory. However, molecules with more than one atom can absorb energy in rotations and vibrations of the molecule. The distance between quantum levels for rotations, and especially vibrations, are much further apart than for translations, so the distribution is more quantized. In fact, for many molecules near room temperature, molecular vibrations are often stuck near the ground state, unable to absorb any energy until much higher temperatures. This leads to a very complex and nonlinear relationship in intramolecular energy with temperature that is hard to predict from first principles, except for simple molecules. As shown in this sketch, even for a simple diatomic molecule like N2, the heat capacity is not constant, but increases with temperature as higher rotational and vibrational states become occupied. Okay, so hopefully at this point I've convinced you that trying to predict potential and kinetic energy from molecular models is a non-starter. This being the case, how do we measure internal energy, or separate it into potential and kinetic energy? Unlike temperature, pressure, or volume, which are directly measurable with an appropriate instrument, there is no such thing as an internal energy meter, at least not yet. So what do we do? This question actually has two components. The first is conceptual. Although we probably won't need to measure internal energy of a substance ourselves, to effectively use data that others have collected, we need to understand the basic structure of these data and how they relate to the quantities we want to know. The second component is more practical. If we have a problem where we need to know the internal energy of a substance or system under a specific set of conditions, how do we go about calculating or modeling this internal energy based on sparse and separate fragments of information collected under conditions far away from our particular problem? This is where first law analysis comes in. The argument goes something like this. Let's say we have a substance in a closed piston cylinder assembly at a particular well-defined reference state with an internal energy U0. For example, maybe we pick 1 atmosphere and 25 degrees C. At this point, we define U0 to have a particular value. Since energy content is relative, it really doesn't matter what value we pick. So in most cases, we just choose the value to be 0. Now imagine we add or remove heat and/or work until the system reaches a new equilibrium state that we care about with temperature T1 and pressure P1. What we'd like to know is what the value of the internal energy U1 is at this new state. How do we measure this or calculate it from previously acquired data? Well, imagine that as we slowly evolve the system from state 0 to state 1, we carefully measure the differential quantities of heat, dQ, and work, dW, per mole that we add to the system at each step along the transformation path from state 0 to state 1. The use of the Greek delta here for differential heat and work is to remind us that while dQ and dW are differential quantities, W and Q are not state properties, so we really can't express these values as a derivative of a function W or Q. Mathematicians call this kind of path-dependent differential quantity an inexact differential. In any case, according to the first law, the differential change in the internal energy during that differential step must be a sum of the differential heat and work added. If we then integrate all these differential changes in U over the transformation path, we get the total change in U from state 0 to state 1. Thus, if heat and work are differentially measurable, internal energy can also be measured. That's basically it. The rest is just details. But of course, you've probably heard the old expression, the devil is in the details. On that note, here's today's cartoon. In this case in particular, it really is all about the details. However, as I hope to convince you shortly, these details contain a lot of insight about how workers characterize heat and work, and the choices they've made in consolidating and expressing their data in a form that makes it fairly straightforward for us to use, not only for internal energy, but other properties, including enthalpy, and as we'll see later, entropy. One of the most important of these details is the transformation path we choose to get from state 0 to state 1. For example, consider the case of a gas. For gases, we often pick a reference state, state 0, at low pressure and high volume, where the gas is ideal. Let's also assume that the state we're interested in, state 1, is a non-ideal gas with smaller molar volume and higher temperature. One possible path we might consider is to compress the gas semi-adiabatically with a piston, which would also tend to raise the temperature due to input of work. We might also need to add or remove a bit of heat to hit our target final temperature, T1. Invoking the first law, we can say that U1 minus U0 is the integral of dQ and dW over this path. In other words, to measure U1, we would need to simultaneously measure both differential heat and work over the entire path. This would require us to record volume, pressure, temperature, and heat flux at every moment in time, and then calculate these integrals. Besides being really hard to do experimentally, we would need a ton of data points to guarantee the accuracy of our integration. Also, the measurement is really hard to generalize. For every end state we are interested in, we would have to adjust our path a little bit and then reintegrate. One way to avoid all this is to recognize that the internal energy is a state property. Recall that this means the value of U1 minus U0 is independent of the path we take from state 0 to state 1. So instead of the composite path I just showed you, where both T and V change simultaneously, what if we instead take a hypothetical path with two distinct legs? In the first leg, we heat the gas at fixed volume to an intermediate state at V equals V0 and T equals T1, called state 2. Then in leg 2, we isothermally compress the gas at T equals T1 to the final volume, V1. In this case, we can calculate u1 minus u0 as the sum of integrals of du over these two path legs. Is this choice any better than the previous path? Examining leg 1, you might notice a couple of things. One is that along this leg, the gas is ideal the entire time. The other is that the volume is fixed. This means PV work is 0. Thus we can write delta U for this leg as an integral of dq only from state 0 to state 2. Some of you might remember that the heat required to heat a substance at constant volume is called the constant volume heat capacity, or C sub V, defined as the partial derivative of U with respect to T at constant volume. This heat capacity is a commonly measured property of an ideal gas and can be separately characterized using bomb calorimetry or other methods. So in all likelihood, it's already been measured by someone. So we probably don't have to do that part of the experiment. That sounds good. Okay, how about leg 2? This leg is a bit more complicated because the gas is not ideal. This means that we'll have both heat and work along this leg. However, this leg is isothermal. Thus, no matter what the work and heat are, what we're describing here is a change in potential energy, while the temperature-dependent components of the intramolecular kinetic energy remain fixed. As described in the previous episode, the difference between the internal energy and the internal energy of an ideal gas at the same temperature is called the internal energy departure and can be readily calculated from measured PVT properties of a gas. If we have an equation of state that we trust for the gas, such as Lee-Kessler, we can calculate this quantity without actually measuring it. So not only is this path easier to think about in terms of our measurement, it's also telling us that if we already have measurements of the ideal gas heat capacity and the PVT properties of our gas in the non-ideal region, there's no point to even making our measurement. Everything we need to know has already been measured. We just need to assemble it for our specific problem. The key to making this work is to choose the right hypothetical path, which best simplifies the problem and puts it in terms of the data or relationships we may already possess or can easily measure with minimal effort. To that end, let's think a bit more about where this is headed. In chemical engineering, we often work with open systems, or systems at defined equilibrium pressure, rather than defined volume. Thus, in many cases, we'd rather work with enthalpy than internal energy. In addition, we are often working with liquids or solids, which are nearly incompressible, but have significant thermal expansion. Unlike a gas, measuring the constant volume heat capacity of a solid or liquid is really difficult because of the enormous pressures that can develop trying to fix the volume. This can make it problematic to have a formalism that revolves around isochoric transformation paths. Instead, imagine in the previous example if we specify the pressure rather than volume, and instead of internal energy, we track changes in enthalpy. Starting at temperature T0 and low pressure P0 in the ideal gas region, we first heat isobarically to an intermediate state 3 at T1 and P0. We then compress isothermally from state 3 to state 1. Since enthalpy is a state property, we can express the total change in enthalpy, H1 minus H0, as the sum of delta H along these two legs. Breaking this down by leg again, we note that along the isobaric path, we must measure the change in enthalpy with temperature at fixed pressure P0. Some of you might recall this is another type of heat capacity, called the constant pressure heat capacity, or C sub P, which is even more widely measured and tabulated than CV is, especially for solids and liquids. In fact, even for gases, the heat capacity correlations reported in our textbook are for CP, not for CV. So in terms of data availability, we're in even better shape than we were along an isochoric path. Meanwhile, along leg 2, isothermal transformation from an ideal gas to a non-ideal gas corresponds to the enthalpy departure, also calculable from PVT relationships and correlated in our textbook for the Lee-Kessler equation of state. So again, it seems that we probably have everything we need to know already. However, even if we didn't, we would probably still not do this experiment. Instead, we'd separately measure the ideal gas heat capacity and PVT properties, and then use this information to calculate enthalpy and other conditions we've not measured. The real power of state property relationships and the first law is that they allow us to make widespread predictions of properties under all kinds of conditions based on just a few key measurements. Before proceeding with some examples, I'd like to first highlight a few limiting cases that tend to arise quite often, so deserve special attention. These examples also lead to some useful canned relationships you can use in general practice. The first is the case of an ideal gas. As discussed in the previous episode, the potential energy in an ideal gas is zero by definition, so the internal energy is only a function of temperature. Since PV equals RT for an ideal gas, the enthalpy is also only a function of temperature. Recalling the analysis we did of delta U and delta H from state 0 to state 1, and setting the departure terms to 0 for an ideal gas, we find that delta H and delta U are independent of pressure, and differ only in which ideal gas heat capacity is being integrated from T0 to T1. Recalling that H is U plus PV, and recognizing that delta PV is R delta T for an ideal gas, we can also conclude that delta U and delta H differ by R delta T. Combining this with the expressions above, this further implies that for ideal gases, Cp is Cv plus R. In other words, Cp and Cv are not really separate properties. This is why our text only provides a correlation for Cp for ideal gases. Another important limiting case is incompressible liquids and solids that have nearly pressure-independent molar or mass-specific volume. For a dense phase, the internal energy will be composed of kinetic energy, which is a function of temperature, and potential energy, which is a function of volume. This means that if the volume is independent of pressure, the internal energy will also be independent of pressure. Meanwhile, the enthalpy will be given by U plus P times V0, where V0 has a nearly constant small value. At low pressure, the entire PV term will be small, such that U and H are approximately equal to each other. In this case, both delta H and delta U will be equal to the integral of Cp dt. At higher pressures, adding the two legs of our hypothetical path, the enthalpy will scale linearly with pressure as V0 times P minus P0. Many textbook authors construe the equivalence of delta U and delta H at low pressure to mean that Cp and Cv are approximately equal for dense phases. This is a well-entrenched myth that conflates the incompressibility of a liquid or solid with its thermal expansion, which is usually not negligible. This expansion can absorb massive amounts of energy, causing Cp and Cv to differ by as much as 30 to 40%, for example, polymers and hydrocarbon liquids. The reason U and H are nearly the same at low pressure is because liquids and solids have a small specific volume, not because Cp equals Cv. Finally, a third important limiting case is the change in enthalpy of a single component substance during a phase change, such as boiling of a liquid. Due to the loss of degrees of freedom, the pressure remains constant during the phase change at a given temperature. Thus, delta H is delta U plus P0 times delta V, where P0 is the pressure of the transition. But if we calculate the PV work for an isobaric transformation in a closed system at pressure P0, it is minus P0 times delta V. Thus, after applying the first law, we find that the heat added to the system during the transformation is equal to the change in enthalpy. This is why the enthalpy of vaporization is often called the heat of vaporization. Arcane terminology, but technically true for an isobaric transformation. The consequence of this is profound. It means that to determine the change of enthalpy at a phase transition, we do not need to worry about actually measuring or calculating the work. We only need to measure the heat input to determine the difference in enthalpy between the two phases. This applies to any isobaric phase transition we want to think about: liquid gas, solid liquid, solid gas, solid alpha to solid beta, as well as reactions. Okay, so let's go through a couple of examples where we use sparse data along key legs of a hypothetical path to calculate the enthalpy of a real substance. The first example is gaseous hexane at 225 degrees C and 23.7 bar. To get us started, the enthalpy of vaporization at the normal boiling point of hexane at 68.7 degrees C is 28.86 kilojoules per mole. Based on this, let's try to calculate the enthalpy under the conditions of interest. First, before we can draw a hypothetical path, we need to decide on a reference state. Let's say we select 25 degrees C in 1 atmosphere, where hexane is a liquid. Defining this as having zero enthalpy, our goal is to construct a hypothetical path to our endpoint that follows lines of known data. Since we know delta H of vaporization at 1 atmosphere, one thing we could do here is to first heat the liquid at 1 atmosphere to the boiling point. To calculate delta H for this leg, we would need to know the heat capacity of the liquid. Checking the textbook, it looks like this one is available, and only one term, meaning constant Cp. Next, we can boil at 1 atmosphere, taking us to a gas at the same temperature. That's what we already have data for. From there, we can heat the gas to 225 degrees C. Since it's only 1 atmosphere, we can probably assume it's close to ideal. For hexane as an ideal gas, the textbook provides a 3-term polynomial correlation for Cp. Finally, as a last step, we need to isothermally compress to 23.7 bar. For this, let's use the Lee-Kessler departure tables. Thus, after adding the critical properties, our model involves a total of 8 measured parameters. Working through the numbers, delta H along leg 1 is given by a constant heat capacity times the difference in temperature between 25 and 68.7 degrees C, for a net change of 8.61 kilojoules per mole. Along leg 2, the boiling of the hexane we already have, 28.86 kilojoules per mole. So this one we get for free. Along leg 3, we need to first integrate the 3-term polynomial heat capacity, spanning the boiling point up to 225 degrees C. Plugging in numbers and calculating, we obtain 29.36 kilojoules per mole. Finally, for leg 4, we need to look up the critical properties and eccentric factor for hexane. Calculating the reduced temperature and pressure, 0.98 and 0.80 respectively, we can see that we'll have a near critical gas. Turning to the Lee-Kessler charts, we find a 0th order enthalpy departure function of minus 1.27. Repeating for the first order correction, we find a value of minus 1.32. Multiplying by the eccentric factor and adding, we end up with a total departure function of minus 1.66, which after multiplying by RTC yields a total enthalpy departure of minus 7.0 kilojoules per mole. Finally, after putting everything together for the 4 legs, we have a total enthalpy of 59.8 kilojoules per mole, which is within about 2% of the value calculated from the NIST database. As a second example, let's calculate the enthalpy of ice at minus 30 degrees C and 60 bar, based on knowing the enthalpy of fusion at 0 degrees C. First, let's adopt a reference state of H equals 0 for liquid water at 0 degrees C. This is the same choice as the steam tables. Thus, to get a solid at 60 bar, we would need to freeze somewhere. Since we know the enthalpy of fusion at 0 degrees C, it makes sense to do that first. We can then cool to minus 30 degrees C as a solid. This requires the heat capacity of ice, which appears in our textbook as a 1-term constant heat capacity. We can then compress to 60 bar. If we assume the density of ice is approximately constant, we can take delta H to be V delta P, where the mass-specific volume of the ice is the reciprocal of the density of ice. Working through numbers again, we get a total enthalpy of minus 385 kilojoules per kilogram. This is slightly higher than ice at minus 30 degrees C and 1 atmosphere, reflecting the significant role played by the PV term for dense phases when pressure becomes very high. As we'll see later, this has an impact on the melting point. Hopefully these examples helped illustrate some of the practical nuts and bolts of how to draw on existing thermodynamic data to determine H and/or U over a range of conditions and situations. As we'll see in the coming weeks, we can use the same basic approach of constructing a hypothetical path and integrating changes in properties along legs of that path to calculate other properties like entropy and free energy without having to do any additional experiments. This is the real power of first law analysis, and why we spend so much time focusing on it.